There is a universe you can see, a brilliant tapestry of stars and light painted across the endless dark canvas of space. And then there is the other universe, the one that whispers just beyond the edge of our perception, holding everything together. We have given this great cosmic secret a name, a placeholder for our own profound and humbling ignorance about existence. We call it dark matter, not because it is evil or menacing, but because it gives off no light for us to see. It is the ghost in the cosmic machine, the silent partner to every star, every galaxy, every cluster that we can observe. For every speck of dust and every burning sun we can account for, there is 5 times as much of this other, stranger stuff. Imagine the entire universe as a vast, dark ocean, and everything we know is just the shimmering foam on the surface. The great cosmic structures, the galaxies that spin in majestic spirals, are behaving in a way that defies our known laws. They spin too fast, far too quickly to hold themselves together with the gravity of the stars and gas we can measure. Something else must be there, an unseen mass, a gravitational anchor preventing them from flying apart into the void. This was our first clue, the first hint that the cosmos was hiding its true weight from our most powerful instruments. We are searching for a phantom that passes through solid walls, through planets, and even through our own bodies without a trace. It does not interact with light, it does not feel the electromagnetic force, it simply exists, exerting its silent, powerful pull. The story of dark matter is not a story of discovery, but a story of a search, a grand quest for the invisible. We are chasing a shadow, guided only by the subtle ways it bends and warps the very fabric of space-time around it. Think of it as a vast, invisible scaffolding upon which the visible universe was built, the framework for all creation. Without this hidden substance, the beautiful galaxies we admire would never have formed in the first place. They would be formless clouds. This invisible matter clumped together first in the early universe, creating the gravitational wells for normal matter to fall into. Every galaxy we see, including our own Milky Way, sits nestled within a massive spherical halo of this dark material. We are adrift in an unseen ocean, a river of dark matter flowing silently through our solar system, through our world. So how close are we to finally seeing this ghost? To unveiling the greatest secret the universe has kept from us? We look for it deep underground, in laboratories shielded from the cosmic radiation that bombards our planet's surface every second. Here, in the profound quiet and darkness, scientists wait patiently for a single, rare collision, a tiny whisper of interaction. They are listening for the faintest sound in a silent cosmos, a message from the 85% of the universe we cannot see. Other scientists look outwards, using the entire universe as their laboratory, searching for clues in the most violent cosmic events. They hope that when 2 supermassive objects collide, they might produce a particle of dark matter that we could finally detect. We are also building machines of incredible power on Earth, particle colliders designed to recreate the conditions of the Big Bang. In these fleeting moments of immense energy, we hope to forge a particle of dark matter into existence, if only for an instant. The search is a testament to human curiosity, our relentless drive to understand the fundamental rules of our own reality. To solve this puzzle is to rewrite our understanding of cosmology, of gravity, and of our own place in the grand cosmic design. What if dark matter is not one thing but a whole family of strange particles, a dark periodic table of elements? A universe that mirrors our own, interacting only through gravity, existing in the same space but in a different way. Could it be a force we have not yet discovered, a modification to gravity itself over vast cosmic distances? Perhaps our understanding of the universe's most fundamental force is incomplete, a mere approximation of a deeper truth. The search for dark matter is forcing us to question the very foundations of physics, to be humble before the cosmos. Every star chart is incomplete, every map of the universe is missing the largest and most important continent of all. We are like ancient cartographers, drawing maps of a new world with vast, unexplored regions labeled, "Here be dragons." But these are not dragons, just a form of matter that plays by a different set of rules, a different cosmic game. Its presence is inferred, not seen. like the wind that rustles the leaves of a tree without revealing its own form. The gravity of galaxies acts as the leaves, and their impossible speed is the rustling that tells us the wind is blowing. We are closing in, slowly, patiently, from many different directions, shining our little lights into an immense darkness. Each null result, each experiment that finds nothing, is still a victory, because it tells us where the ghost is not. We are narrowing the search, eliminating possibilities, drawing the box tighter around this profound and beautiful mystery. The secret of dark matter is not buried in a distant galaxy. It is all around us, flowing through this very room. Answering this question will not just be another discovery, it will be a form of cosmic awakening for our species. It will be the moment we finally realize that the universe we perceived was only a fraction of what is truly there. The universe is not empty. It is full of something we are only just beginning to comprehend with our limited senses. The journey to understand it requires a quiet mind, a sense of wonder, and a deep respect for the unknown. Let your mind drift into this immense and peaceful darkness, the silent, invisible architecture that supports all of reality. Here, in the quiet contemplation of the great unknown, we can find a strange and profound sense of peace with the cosmos. Our current proximity to unveiling dark matter is a paradox. We are simultaneously closer than ever, and yet potentially infinitely far. We have confirmed its existence beyond any reasonable doubt through its gravitational effects on galactic rotation curves and the precise mapping of the cosmic microwave background. Yet every direct detection experiment, from the Lux Zeppelin detector deep in a South Dakota mine to the XENONNT experiment in Italy, has returned to quiet, profound silence, ruling out the most promising candidate particles within specific mass ranges. The leading candidates for dark matter particles fall into broad, exotic categories. The most popular for decades have been WIMPs, or weakly interacting massive particles. These hypothetical particles are compelling because their predicted abundance aligns perfectly with cosmological observations, a coincidence known as the WIMP miracle. They would be heavy, slow-moving particles that only interact via the weak nuclear force and gravity, making them almost impossible to detect. Our most sensitive experiments are built specifically to catch the rare, gentle nudge of a WIMP against an atomic nucleus. An alternative and increasingly popular candidate is the axion, a particle that is almost the opposite of a WIMP. Axions would be incredibly lightweight, potentially millions of times lighter than an electron, and they would exist as a vast, coherent wave flowing through the universe. Experiments like the Axion Dark Matter Experiment, or ADMX, use powerful magnetic fields and resonant microwave cavities, essentially trying to tune in to the frequency of the axion field, hoping to convert a stray axion into a single, detectable photon of light. The very act of searching is pushing technology to its absolute limits. We construct detectors using tons of hyperpure liquid xenon or germanium crystals, cooled to near absolute zero to minimize thermal vibrations. These subterranean fortresses are shielded by the Earth itself to block the constant rain of cosmic rays that would create false positives. Every faint signal is scrutinized, every source of background radiation meticulously eliminated, all in the hope of capturing one unambiguous signal from the dark universe, a single atomic recoil in a silent tank. Beyond direct detection, we employ indirect methods, turning our telescopes towards regions of immense density where dark matter should be concentrated. The centers of galaxies, for instance, are predicted to be places where dark matter particles might collide and annihilate each other. Such an event would produce a faint but specific gamma-ray signal. Telescopes like the Fermi Gamma Ray Space Telescope stare patiently at the galactic core, searching for this excess glow that cannot be explained by any known astronomical process, a potential whisper from a dark annihilation. There's also the tantalizing possibility that dark matter is not a particle at all, but a sign that our theory of gravity is flawed. Theories like MOND, or modified Newtonian dynamics, propose that gravity behaves differently on galactic scales, eliminating the need for dark matter entirely. However, these theories struggle to explain the full range of observations, such as the structure of galaxy clusters and the patterns in the cosmic microwave background. Thus, dark matter remains the most elegant and widely accepted solution to the cosmic puzzle. The Large Hadron Collider at CERN represents another frontier in our search, trying to produce dark matter directly. By smashing protons together at nearly the speed of light, we create a shower of exotic particles. If dark matter particles can be created, they would fly out of the detector without interacting, carrying away momentum and energy. Scientists look for events with a significant imbalance, where the energy going in doesn't match the energy coming out, a telltale sign of an invisible particle having escaped into the void. The concept of a dark sector proposes an even richer, more complex reality. It suggests that dark matter isn't a single particle, but a whole family of particles with their own forces, a parallel universe of dark chemistry and dark physics layered on top of our own. This dark sector would interact with our world almost exclusively through gravity, remaining completely invisible and intangible to us. A shadow cosmos whose existence we can only infer from the way it pulls and shapes our own. Another candidate hiding in plain sight could be primordial black holes. These are not the familiar black holes born from collapsing stars, but hypothetical black holes formed in the chaotic, dense environment of the very first second of the universe's existence. If they were created with the right range of masses, they could collectively account for all of the missing mass without requiring any new particles or new physics. We search for them through gravitational lensing events, looking for tiny, brief magnifications of distant stars as a primordial black hole drifts by. The ongoing silence from our experiments is, in itself, a profound piece of data. With each passing year, we rule out more and more of the parameter space where particles like WIMPs were expected to be found. This has forced theorists to become more creative, exploring new ideas and more subtle interactions. The lack of discovery is not a failure. It is a redirection, pushing us away from our simplest assumptions and towards a potentially more complex and far stranger solution to the universe's greatest mystery. The James Webb Space Telescope, while not a dark matter detector, provides crucial context. By peering back to the dawn of cosmic time, it observes the formation of the very first galaxies. The speed and structure of these nascent galaxies are profoundly influenced by the invisible dark matter scaffolding they form within. Studying these baby galaxies allows us to test our models of cosmic evolution, confirming that the gravitational effects we attribute to dark matter have been present since the very beginning of cosmic history. Consider the cosmic web, the largest known structure in the universe. It's a vast, filamentary network of galaxies and gas, stretching across billions of light-years. Our simulations show that this structure is a direct consequence of dark matter. In the early universe, dark matter collapsed under its own gravity into these long strands and dense nodes, and only then did normal matter follow, lighting up the cosmic web with stars and galaxies. We are seeing the glowing decoration, not the immense building it adorns. The bullet cluster provides one of the most direct pieces of evidence we have. This structure is actually two galaxy clusters that have passed through each other. When they collided, the normal matter, the hot gas, smashed together and slowed down, emitting X-rays. But gravitational lensing maps show that the bulk of the mass, the dark matter, passed right through the collision without interacting at all, separating the visible matter from its own gravitational field. It's like seeing the ghost leave the machine. The possibility of warm or hot dark matter has also been explored. Unlike cold dark matter, which is slow-moving and helps form small structures, these faster particles would smooth out smaller density fluctuations. The fact that we observe many small dwarf galaxies orbiting the Milky Way strongly disfavors these models. The universe appears to be built from the bottom up, with small dark matter halos forming first and merging into larger ones, a key prediction of the cold dark matter paradigm. The search is now entering a zero background phase. Future experiments will be so sensitive that even the most minute sources of radiation, like the neutrinos emitted from the sun, will become a significant source of noise. Scientists are developing new techniques, such as directional detectors, that can not only sense a dark matter interaction, but also determine the direction it came from. This would allow them to see a wind of dark matter as the Earth moves through the galaxy's dark halo. Perhaps the most profound implication of dark matter is its sheer dominance. It dictates the structure, evolution, and ultimate fate of our universe. Whether the cosmos will expand forever or eventually collapse in a big crunch, depends on the total density of all matter and energy. Understanding the nature of the dark matter that constitutes a quarter of this total density is not just an academic curiosity. It is essential to forecasting the very end of space-time itself. The mystery of dark energy presents an even deeper puzzle, but it is distinct from dark matter. While dark matter is a gravitational glue that pulls things together, dark energy is a repulsive force that pushes everything apart, accelerating the expansion of the universe. Together, these two dark components make up 95% of the universe's energy density budget, a humbling reminder that all of human history has played out on the stage of the 5% we can actually see. Self-interacting dark matter, or SIDM, is a variation on the Standard Model. It proposes that dark matter particles can, on rare occasions, interact with each other. This could explain some small-scale discrepancies in the observed density profiles of dwarf galaxies. In this scenario, the dark sector is not entirely silent. It has its own faint forces and interactions, creating a universe with a level of complexity that we are only just beginning to imagine, a physics that happens in the dark. Our proximity to the answer could be described as standing before a locked door. We have mapped the size and shape of the room behind it by the sounds we hear and the way the floor settles. We have tried countless keys, the WIMPs, the axions, and none have yet turned the lock. We are now in the process of designing ever more intricate keys, while some are sketching blueprints for a new kind of door entirely, questioning the very nature of the lock itself. The search for dark matter is fundamentally a philosophical quest. It is the modern incarnation of the ancient question, what is the world made of? For centuries we believed it was made of earth, air, fire, and water, then atoms, then subatomic particles. Now we know that the answer is far stranger. It seems to be made mostly of something we cannot name, touch, or see, a substance whose only defining characteristic is its refusal to be known by us. If and when we do detect a dark matter particle, it will be the beginning of a new chapter in science, not the end. We will have to build a new standard model of dark physics. What is its mass? Does it have an antiparticle? Are there multiple kinds? How does it interact with itself? The discovery will open up a dark frontier, a whole new universe of questions that we currently do not even know how to ask. We are in a unique moment of cosmic history, a quiet interlude between the violent formation of the universe and its cold, dark future. In this brief window of stability, conscious beings have emerged and built instruments capable of questioning the very substance of reality. The ongoing search is a race against the accelerating expansion of the universe, which threatens to pull distant galaxies over the cosmic horizon, erasing clues forever. The silence from our detectors might be telling us something fundamental, that we are looking for the wrong thing in the wrong way. Perhaps dark matter's interaction with our world is even more subtle than we imagined. Or perhaps it operates through a force we haven't yet conceived. The challenge is not just one of engineering, but of imagination. We must be prepared for an answer that is not just unknown, but genuinely unknowable with our current concepts of physics. Consider the cosmic neutrino background, a relic of the Big Bang, similar to the cosmic microwave background. These ghostly particles flood the universe, but are incredibly difficult to detect. This proves that the universe can be filled with substances that are almost entirely invisible to us. Dark matter could simply be a heavier, more gravitationally significant version of this phenomenon, a particle that was once a part of the universe's primordial soup, but has long since decoupled from our interactive reality. The symmetries of nature often provide clues to new physics. The WIMP miracle was so compelling because it suggested a deep connection between the physics of the very small, particle physics, and the very large, cosmology. The fact that WIMPs have not been found might indicate that this connection is either more complex than we thought, or that it was a mere coincidence, guiding us down a path that, while beautiful and logical, was ultimately not the one the universe chose to take. As our instruments become more sensitive, we will eventually be able to map the dark matter halos of individual galaxies with stunning precision using gravitational lensing. This will allow us to create a 3D atlas of the invisible universe, testing our theories on the fine-grained structure of dark matter. We may not be able to hold a particle in our hands, but we will be able to trace its gravitational autograph across the entire sky. The feeling of being close to an answer can be an illusion. In 1900, the physicist Lord Kelvin famously stated that there was nothing new to be discovered in physics. Just a few years later, relativity and quantum mechanics shattered that worldview completely. We may be in a similar situation today, standing on the precipice of a revolution in understanding so profound that our current questions about WIMPs and axions will seem as quaint as questions about the luminiferous ether. The surge connects us to the cosmos in an intimate way. The atoms in our bodies were forged in the hearts of stars. But the dark matter flowing through us is something more ancient, a true relic of the first moments of creation. It is a physical link to the Big Bang, a whisper of the universe's origin story that has remained unchanged for 13.8 billion years, waiting for a conscious mind to finally hear it. If dark matter turns out to be a new particle, it would solidify the standard model of cosmology, a triumphant confirmation of our scientific method. But if it turns out to be a modification of gravity, the implications are arguably even more profound. It would mean that the most familiar force in our lives, the one that holds us to the Earth, is not what we thought it was, and that its true nature is only revealed on the grand stage of the cosmos. Some fringe theories even connect dark matter to consciousness, though this is far outside the realm of mainstream science. The idea that this invisible, pervasive substance could be the substrate for a different kind of existence is a compelling thought. It reminds us that our definition of life and reality is based entirely on the 5% of the universe we can perceive, leaving the nature of the other 95% to pure, unbridled speculation and wonder. The resolution to the dark matter mystery will likely not come from a single eureka moment, but from a slow convergence of evidence from multiple independent lines of inquiry. A faint signal from an underground detector, combined with an anomalous gamma-ray glow from a dwarf galaxy, and a peculiar pattern in the distribution of the first stars, all pointing to the same new physics. It will be a gradual unveiling, a slow dawn of a new cosmic understanding. Every time you look up at the night sky, you are looking through a transparent ocean of dark matter. It is in the space between the stars it envelops the entire galaxy, and it stretches out into the intergalactic void. The light from the most distant quasars has traveled for billions of years through this substance to reach your eyes. Its presence is a constant, silent companion to every photon on its journey across the universe. The pursuit of dark matter is an act of collective patience. Generations of scientists may dedicate their entire careers to this single problem. Some build the theories, others design the experiments, and others still will analyze the data. It is a multi-generational relay race, with the baton of knowledge being passed down, all for the chance to be the ones who finally draw back the curtain on the true nature of our universe. What if the interaction is so weak that we could never build a detector large enough or sensitive enough to find it? It's a humbling thought that the universe may contain secrets that are fundamentally beyond our technological reach. In this case, dark matter would remain a ghost, its existence confirmed only by its gravitational shadow, a permanent and profound testament to the limits of our empirical exploration of reality. The strange behavior of certain galaxies, like Dragonfly 44, which appears to be made almost entirely of dark matter, challenges our models. Conversely, galaxies have been found that seem to have very little dark matter at all. These outliers are crucial pieces of the puzzle, suggesting that the relationship between dark matter and normal matter is more complex and less uniform than our simplest theories predict, offering tantalizing clues for the next generation of theories. Imagine trying to understand what water is by only observing the motion of ships on its surface. You could infer its currents, its tides, and its depth, but you could never know its chemical composition. This is our situation with dark matter. We are mapping its gravitational currents and tides with exquisite precision, but we are waiting for the moment when we can finally scoop up a single drop of the ocean itself for study. The final answer, whatever it may be, is guaranteed to be astonishing. It will either reveal a new building block of the universe, a particle that has been hiding in plain sight for all of eternity, or it will force us to reimagine the very fabric of space-time and the nature of gravity itself. There is no mundane outcome. The end of this search promises a fundamental shift in our perception of the cosmos. We are closing in on the WIMP. The parameters for its existence are shrinking. We are also closing in on the axion. with new experimental designs poised to scan a much wider range of possible masses. The walls are closing in from all sides on this mystery. While we cannot say if the final revelation is years or decades away, we can say with certainty that we are in the endgame of the initial search. It's possible the secret of dark matter is entangled with the secret of the universe's beginning. The processes that occurred in the first fraction of a second after the Big Bang, an era of physics so extreme we can only speculate about it, likely forged the dark matter and set its abundance. To understand dark matter is to open a direct window onto the moment of creation itself, a glimpse into the cosmic crucible. So how close are we? We are as close as a dreamer on the verge of waking. The shape of reality is still hazy, but we sense a profound truth is about to snap into focus. We are living in the final moments of cosmic ignorance, on the cusp of seeing the universe not for what we thought it was, but for what it truly has been all along: vast, mysterious, and mostly dark. The search for dark matter teaches us a quiet humility. It reminds us that our senses are profoundly limited, evolved only to perceive a thin slice of reality relevant to our survival on a single, small planet. To comprehend the universe, we must build new senses from metal, crystal, and silicon, extending our minds into realms that nature never intended for us to see, patiently listening for a whisper from the silent majority of creation. The universe is under no obligation to make sense to us, or to be discoverable by us. The fact that we can even pose the question of dark matter is a triumph of reason and observation. Every night that an experiment runs in the deep, silent Earth is an affirmation of our unyielding curiosity, our refusal to accept the visible as the final word on reality. The quest itself is a source of meaning. The dark matter that holds our galaxy together is not static. It is a dynamic, shifting halo, with streams of dark matter from consumed dwarf galaxies still flowing through it like currents in an unseen sea. Our solar system is currently passing through one of these streams, meaning the dark matter wind we are trying to detect might be blowing from an unexpected direction, a detail that could be crucial to its eventual discovery. Gravitational waves offer a completely new way to probe the dark universe. The collision of two dark matter-rich objects, such as primordial black holes or even hypothetical dark matter stars, would release ripples in space-time that we could detect. This would be a way of hearing the dark sector, even if we can never see it, providing a new sense for exploring the 95% of the cosmos that remains invisible to light. The answer to the dark matter puzzle is not just out there in the cosmos. It is passing through you right now. Billions of dark matter particles are likely streaming through your body every second, utterly oblivious to your existence, just as you are to theirs. You are a ghost to them, and they are a ghost to you. The quest is simply to find a way to make these two separate realities finally acknowledge one another. Ultimately, the question, how close are we, is a human one, framed by our sense of time and progress. For the universe, the secret of dark matter is not a secret at all. It is simply a fact of its own existence. The dark matter has been here for 13.8 billion years, patiently waiting in the dark, holding the galaxies in a silent gravitational embrace, indifferent to whether we ever find it or not. Let your mind settle on this profound truth. The universe is mostly not what you see. The stars are just the crests of an unimaginably vast and deep ocean of reality. Contemplating this invisible immensity is not a cause for fear, but for awe. It expands the boundaries of our reality, inviting us to imagine a cosmos far richer, stranger, and more wonderful than we ever thought possible. We are on a threshold. The great experiments of our time are pushing into the last well-motivated corners where this hidden particle might reside. A discovery could come tomorrow, or in a decade, but it feels inevitable. We are approaching the edge of the map, the point where the familiar world ends and the vast, dark continent begins. We are drawing closer to the shore of the invisible. The silence of the universe is not an absence, but a presence. It is the quiet hum of dark matter holding the cosmos together. The darkness is not emptiness, but a substance we cannot yet perceive. As you drift into stillness, feel yourself becoming part of this immense, invisible structure, a conscious speck of dust resting on the silent, powerful framework of reality itself. Our proximity to the answers measured not in miles or years, but in understanding. And with every passing moment of quiet contemplation, with every question we dare to ask of the silent darkness, we move one step closer to unveiling the profound and beautiful secret that the universe has been keeping, waiting for us to finally learn how to see in the dark.